In this section, we're going to talk about what's called the normal distribution. And this is a very common type of distribution that is represented by a bell-shaped curve. And this normal distribution arises in a lot of data sets that concern human characteristics. For example, distributions of men's or women's heights tend to be normal, and standardized tests seem to be normal. All normal distributions have certain characteristics, and I have them listed here. So most data values near the mean giving the distribution of a well-defined single peak. So most of the data values being near the mean means it's going to look something like this. The mean is going to be in the center, and most of those values are going to be near the center. Now, the variation can change and the value of the mean can change, but the shape of the distribution, if it's normal, is going to be a bell-shaped looking curve. Okay. The second condition is that data values are spread evenly around the mean, making the distribution symmetric. Now, it doesn't have to be exactly symmetric because most data in real life is not going to be exactly symmetric, but it should look somewhat symmetric, where if you cut it up the middle at the mean, it should look about the same on either side. Larger deviations from the mean become increasingly rare, producing tapering tails of the distribution. That's our third condition. And what we mean by that is where most of the data is in the center, there's some rare values off to each side that create these tails. And then the last condition of a normal distribution is that one standard deviation occurs at the inflection point. And what I mean by that is an inflection point is where the graph turns from concave up to concave down or vice versa. So if you notice, our inflection point in this graph A seems to be about right here, because if you notice, let me do this in a different color, this part of the graph is concave down, while this part of the graph is concave up. So I would say that this approximately is our inflection point. And what that means, when the graph starts to change concavity, that's where you have one standard deviation out from the mean. So from the center, which is your mean, in this case the mean is 75, from the center out to the inflection point would be one standard deviation. And that goes in the other direction too, one standard deviation this way as well. Now, the larger the standard deviation, the more wide and spread out that graph is. If you notice in graph B, our inflection point looks to be about right here. This part here looks concave down, and then this part here looks concave up. Now, the standard deviation for this would be from here to here. The wider the standard deviation is, the wider that bell curve is going to be. So it looks like this standard deviation is greater. Because this graph is more wide, where this graph here is more centered or closely huddled to the mean. Now, they both have that same bell curve shape, but one graph is a little bit wider than the other, and the wider the graph, that means the bigger the standard deviation and the more spread out the graph is. In this example, it's giving us two sets of data and asking us if either of these distributions would be considered a normal distribution. And so if I look at the data of graph A, it's the chest circumference measured of Scottish militiamen in inches. And if you notice, if I take my pen and I go across and I make a continuous curved line across the tops of these bars, I get what looks like a normal curve. It's a bell-shaped curve. The center would be the mean, and I have two tails on the end with the rare values. So I would definitely consider this normal because it has all those conditions that we talked about that the shape of a normal graph needs to have. Now, when I look at the second graph that has some data values for population density, if I connect the tops of all of those bars to see what that shape looks like, this is the graph of data that is skewed right. Because it has that shape where most of the data lies to the left, and then it has some values to the right that cause that line to be pulled, and it looks like it has an arrow pointing to the right. In this example, we have a description of data sets, and we're going to decide if we think it's going to be normal or not. So we're looking at it in terms of verbal descriptions in this example, and the previous example we talked about it graphically. In this example, we have two verbal descriptions of two different data sets, and is asking if you think it would be a normal distribution or close to a normal distribution. Part A says scores on a very easy test. Well, if I had scores on a very easy test, most likely we would have a lot of high scores and very few, if any, low scores. The graph of that, if I graphed where I have 100% over here, 0% over here, most of my values would be high. So most of my values would be over here, and then I would have a few low values close to 0, if any. So I would say that this data set would be skewed left. For shoe sizes of random sample of adult women, usually when it comes to characteristics of the human body, like height, weight, shoe size, arm length, leg length, head circumference, all those kinds of things, usually those are normally distributed because most women are going to have, if you look at them, there's going to be like an average shoe size for women. And then you're going to have some extreme values that are high and some extreme values that are low. So you'll have your average in the middle where most of the data falls in here, and then you'll have some extreme values on either end. So this I would definitely call a normal distribution, or close to normal distribution. It's never going to be perfectly symmetric. Now, because all normal distributions have the same bell shape, we can characterize the variation of any normal distribution with just a single number, the standard deviation. And we talked about that in the previous section. The standard deviation is a number that we calculate, and the bigger that standard deviation, the wider the graph is going to be, and there's going to be more variation. The smaller the standard deviation is, the smaller or the less wide that graph is going to be, and it's going to be more centered around the mean and huddled closer to that mean. Now, a simple rule that we call 68, 95, 99.7 rule for a normal distribution gives precise guidelines for those percentage of data values that lie within 1, 2, or 3 standard deviations away from the mean. Now, I grew up calling it the empirical rule because I feel like 68, 95, 99.7 rule is a mouthful. So if you hear me use the word empirical rule, it's the same thing. So I'm going to put on here AKA empirical rule. Okay, so what the empirical rule tells us is the farther away you are from the mean, if you're looking at it in terms of an interval between one standard deviation on an interval from one standard deviation on the left side of the mean to one standard deviation on the right side of the mean, that interval between those two values, you'll have about 68% of the data. And that's what this is right here. The mean is always in the middle. And then if I come out one standard deviation in either direction from the mean, about 68% of the data is going to fall on that interval. So this is going to be approximately, these points here that I'm just drawing here, this is approximately the inflection point. Because that's where we have our first standard deviation out in either direction from the mean. Now, the rule says if I come out 2 standard deviations away from the mean, I'll use a different color, I'll use blue. So here's the mean. If I come out 2 standard deviations in this direction or in this direction, there'll be about 95% of the data that will lie on that interval. And then the third value is if I go out 3 standard deviations from the mean. So here's the mean. If I come out 3 standard deviations from here to here, about 99.7% of the data is going to fall on that interval. So that's why the rule is called, right up here, the 68, 95, 99.7 rule, because those are the percentages as you go out 1 standard deviation, 2 standard deviations, and 3 standard deviations. Now, when we get into more specific examples, you'll be able to see why this is a useful rule to learn. So let's jump into our first example. Each test that makes up the verbal or the critical reading and mathematics parts of the SAT is designed so that its scores are normally distributed. So here's the key word. As soon as I see normally distributed, I know our data is going to have a bell-shaped curve. The mean is 500 and it has a standard deviation of 100. Interpret this statement according to the 68, 95, 99.7 rule. So I apologize ahead of time because I'm a horrible artist, so you'll just have to visualize that this looks good. But here's our normal curve. The mean always goes in the middle, and it tells us here that the mean is 500. So that's our average test score, 500. Now, if I go out 1 standard deviation, that's at that inflection point. So that's where the graph turns from concave down to concave up, which I can visualize to be maybe about right here. Again, I'm a horrible artist, so this isn't drawn to scale. This isn't perfect, but you can, I'm hopefully drawing it well enough that you can understand what I'm doing here. So that means if this is the mean at 500, and I come out 1 standard deviation this way, I'll label it as 1S for 1 standard deviation in either direction. It says in the question, or in the statement here, that the standard deviation is 100. So that means every time I come out 1 standard deviation, that's a scale that represents 100. So if I come out 1 standard deviation to the right, think of this as a number line. If I go 500 or if I start at 500 and I go 1 standard deviation to the right, since 1 standard deviation represents 100, this is going to be 600. If I come out 1 standard deviation to the left, looking at this as a number line, I'm going down in numbers, so this is going to be 400. Now I'm going to label this, let me fix this. I'm going to label this as minus 1 standard deviation because I'm going to the left. So the minus only indicates the direction that I'm heading in. It doesn't mean anything other than that. So then I'm going to label this as 400. Now, if I go out a 2nd standard deviation, that means I'm adding another 100. So from here to here is 100. So that means this is going to represent 700. And if I go out another standard deviation to the left, I'm subtracting another 100 because I'm going to the left where my numbers are getting smaller. So this is going to be 300. Okay, now the last one, that doesn't mean there's no more than 3 standard deviations on a graph. It just means that's where this rule stops. There can be 4, 5, 6 standard deviations. However, most everything is going to lie within 3 standard deviations. So this is what the rule covers, 1, 2, and 3 standard deviations. So if I go out a third standard deviation, going to the right, I'm adding numbers because I'm going to the right, and that means we're increasing our numbers. So that would be a score of 800. And if I go to the left, my numbers are decreasing by 100, so that's going to be 200. Now, here's our picture for 1, 2, and 3 standard deviations. In fact, let me write that in here. There's -1 standard deviation, -2 standard deviations, -3 standard deviations. And on this side, we're adding standard deviations. I'll abbreviate it ST for standard deviation. Now, what the rule says is that 68% of the data will lie within 1 standard deviation of the mean. So that means if I look at just going out 1 standard deviation from the mean, from here to here, that means approximately 68% of the data is going to lie between 400 and 600. So we're going to write down, according to the rule, approximately 68% of SAT scores lies between 400 and 600. Okay, now going to the next standard deviation out. If I go 2 standard deviations out, that's between 300 and 700. So I would say approximately 95% of SAT scores lies between 300 and 700. Then lastly, for the last rule, I would say approximately, because that last rule talks about going 3 standard deviations out, that would be 99.7%. I would say approximately 99.7% of SAT scores lies between, and that would be between 200 and 800. Which makes sense because the wider range of scores you have, the more data values that are going to fit in that score. Okay, in this example, it says vending machines can be adjusted to reject coins above and below certain weights. The weights of legal U.S. quarters are normally distributed. Here's our key word, so we know we're dealing with the bell-shaped curve. They are normally distributed with a mean of 5.67 grams. So there's some key information. And a standard deviation of 0.07 grams. So there's some more key information. I'm going to highlight all of those. If a vending machine is adjusted to reject quarters that weigh more than 5.81 grams and less than 5.53 grams, what percentage of legal quarters will be rejected by the machine? So these machines are set up to try to make sure that the coins they're getting are valid. But there may be some coins that are authentic but get rejected because of their weight. So what we're going to do is use the normal curve to figure this out. So we know we have a normal curve because it tells us it's normally distributed. So I have this kind of a shape. The mean always goes in the center, and it says the mean is 5.67 grams. So this is represents, on here on the horizontal axis, represents the grams of the quarters. Okay, now it says the standard deviation is 0.07 grams. So that means every time I make a tick mark out to the right, I'm going to add 0.07 grams, and each of those tick marks will represent a standard deviation. So if I add my standard deviations to the right, that means I'm going to be adding 0.07 each time. So if I add 0.07 to 5.67, that gives me 5.74. Then if I add it again, that gives me 5.81. And then if I add 0.07 one more time for 3 standard deviations out, that gives me 5.88. Now if I go in the other direction where it's less than 5.67, if I subtract 0.07 grams, that's going to give me 5.6. And if I go out another standard deviation, that's going to give me 5.53. And if I go out one more standard deviation to the left, I get 5.46. Now that doesn't mean, I want to stress, that doesn't mean there's no more standard deviations going either right or left, but that's what this rule covers. It covers 1 through 3 standard deviations. Okay, so what we are looking for is the percentage of legal quarters that will be rejected by the machine. So anything that is between 5.81 and 5.53 is going to be accepted. So these coins in here with these weights are good. These will be accepted. But anything to the right that's higher than 5.81 or lower than 5.53 is going to be rejected. So we've got to figure out what percentage is going to be rejected. If I know that going out 2 standard deviations in either direction using my 68, 95, 99.7 rule, going 2 standard deviations out in either direction gives me 95% of the data. So from here to here, in this accepted area, this is 95% of the data, which means the portion that's not accepted is going to be 5%. So the answer to this is approximately 95% will be accepted and 5% will be rejected. Okay, the next example says, a survey finds that prices paid for 2-year-old Ford Fusion cars are normally distributed. So here's our keyword again, so we know it's going to be a bell shape. It has a mean of $17,500 and a standard deviation of $500. Consider a sample of 1,000 people who bought the 2-year-old Ford Focus or Ford Fusions. So it says how many people paid between $17,000 and $18,000. So we're going to use our empirical rule to figure this out. So here's our picture. Again, sorry about my artistic skills. Since it's normally distributed, we're going to have that bell-shaped curve. The mean, which is 17,500, goes in the middle. And we have a standard deviation of 500, which means every time we make a tick mark to represent one standard deviation out in either direction, that's going to be worth $500. So we're going to go out $500 in either direction, and that's going to give us $18,000 and $17,000. So from here to here is 500, and from here to here is 500. Now the question asks, how many people paid between $17,000 and $18,000? Well, if I look, that's one standard deviation out in either direction, And according to our rule, that covers 68% of the data values. In this case, we're talking about people that buy these Ford Fusion cars. Because it says 10,000 people in this question bought these cars, and we want to find how many paid between 17,000 and 18,000, and we know that that's 68%, so we're going to take 68% of 10,000 people. When we do that, remember when you're finding a percentage of something, you put it in decimal form and you multiply. So I take 68 times 10,000 and I get 6,800 people. Okay, now the part B says how many people paid less than 17,000. Well, if I look at this bell-shaped curve again, 17,500 is in the middle, and we know if we went one standard deviation to the left, that gave me the 17,000, and the question is asking how many paid less than 17,000, so we want to see what this portion of the graph represents, what percentage. Well, we can figure this out because I know from the previous part that if I go 500 to the right, that's going to give me 18,000. I know 68% is one standard deviation out in either direction, which means there is 32% that is in those tails. So 68% of the data is in the middle, and then what's left over that isn't in that center 68% is 32%. And I got that by just seeing what's left over from 100%, right? 100% minus 68% is going to give me 32%. So the two shaded areas should add up to 32%. Well, we only want to know the shaded part to the left of 17,000, which is that blue shaded area, because normal curves are symmetric. Each of these areas should be the same, which means I just need to take that 32% and divide it in two. So this area here is 16%, and this area here is 16%. So that means the area to the left of 17,000 is 16%. And I can check it by adding it all up. All of it should add up to 100%. If I take 16% plus 68% plus 16%, that's a total of 100%. So I know that 16% of 10,000 people paid less than 17,000. So if I take 16% of 10,000 people, that's going to give me 1,600 people. Okay, last part. How many people paid more than 19,000? So if we make that bell-shaped curve, in the center we have 17,500. In order to get to 19,000, I have to go out 3 standard deviations because each standard deviation represents 500. The first standard deviation is at 18,000. The next standard deviation is at 18,500. And then the third standard deviation is that 19,000. So we're looking for this small portion of people and this little tail right here that paid a lot of money. So these are going to be the extreme values. Well, I know if I go out 3 standard deviations in either direction, that's going to cover from here to here, based on our rule, that's going to cover 99.7% of the data, which means 0.3% of the data is what's left over. Those are the little tails at the end, because I would take 100% minus 99.7%, and that would give me 0.3%. So I know those two tails in either direction, this one over here, the the tail to the left and the tail to the right should add up to 0.3%. But since I'm only looking at the top highest tail, this tail here, I got to split 0.3% into 2. So I know that this little tail right here covers 0.15% of the people that bought this car. It's the top extreme values. So I got to find 0.15% of 10,000 people. And those are going to be the people that paid more than $19,000. Well, if I take 0.15% of 10,000, I get 15 people. So that means of all of those 10,000 people, approximately 15 people are going to pay that extreme high value of 19,000 or over. Okay, so now we're going to talk about standard scores, and the 68, 95, 99, 7 rules applies to when data values that are exactly 1, 2, or 3 standard deviations away from the mean. But there are other times that you might want to know something like when you're 1.5 standard deviations away from the mean, or 1.3 standard deviations away from the mean that aren't exactly 1, 2, or 3 standard deviations away from the mean. And when we want to be able to do this, what we use is what's called standard scores, which we sometimes call z-scores, and it's abbreviated by the letter Z. So we're going to put down that Z stands for standard scores, and this tells us how many standard deviations away from the mean we are. So these tell us how many standard deviations away from the mean we are, and it could be something other than 1, 2, and 3. It could be 1.5, and if it's negative, that just means that it's on the left side of the mean. Now, if we're talking about the raw scores, then we typically use X. Or I should say raw scores or values. Okay, so what I mean by this is in the previous example, when we talked about SAT scores, we had 500 in the middle, which was the mean, and then we had 100 was the standard deviation. So as we came out, 1 standard deviation to the right, that was 600. 2 standard deviations would give us 700, and then 3 standard deviation would give us 800. And then if we went to the left, that's minus 1 standard deviation because we went to the left, that was 400. Minus 2 standard deviations to the left would give us 300. And then minus 3 standard deviations to the left gave us 200. These are our raw values or our raw scores. If I specifically said I wanted Z to be 1.5, that means I'm coming out 1.5 standard deviations away from the mean. And that's our Z-score. That's when it's standardized. When we don't give us the specific values, we're just saying how many standard deviations it is from the mean. So this would be an example of when we use X's for raw scores. And our raw scores are these values here. Right, our actual scores. But when we talk about standardizing the normal curve, what we would do, this would be our Z's when we standardize. The center would always be 0 because our Z represents how far away we are from the mean. And if we're at the mean, there's no distance, so we would call that 0. Z would be 1 if we're 1 standard deviation away from the mean to the right, and then Z would be negative 1 if I'm 1 standard deviation to the left. this would be a 2 because I'm 2 standard deviations away. On the right, this would be -2, and so forth. So in this case, when we're using this specific example, z equals 0 corresponds to a score of 500. Z equals 1 standard deviation away from the mean corresponds to 600. Z of -1 corresponds to 400, etc. So if I ask you if z is -2, what's my value of x, or my Roth score? If I look at -2, that means I come 2 standard deviations out to the left. That means I would be sitting at a score of 300. So when we talk about standardizing, we're only talking about how many standard deviations we are away, but not the actual score or the actual value that's on the graph. Now, to compute your standard score, to figure out what your z is, you would take whatever your data value is, subtract your mean, and then divide by the standard deviation. So using this example up here so that it can make sense, let's say I wanted to figure out, so I'll use this as an example. Let's say I wanted to figure out, if I had a score of 350 and I want to figure out how many standard deviations away from the mean that would be, and that means I want to figure out what my value of z is. So I would take my data value, which would be the 350. I would subtract my mean. Remember, my mean was 500. And I would divide by my standard deviation. My standard deviation was 100. Because I'm using this example up here of my scores where my standard deviation is 100, my SAT scores, and my mean was 500. So when I do that, I'm going to get -150 over 100, and when I divide, I'm going to get -1.5. So this tells me I'm 1.5 standard deviations away from the mean, and the negative tells me I'm on the left side of the mean, which makes sense because at 350, if I look back up here, if I come out 1.5 standard deviations away from the mean, it's between 300 and 400, which would be 350. So using this formula here, we can figure out how many standard deviations away from the mean we are by calculating what our value of z is. Okay, let's do another example. The Stanford-Binet IQ test is scaled so that the scores are normally distributed, with a mean of 100 and a standard deviation of 16. Find the standard scores for the IQ scores of 85, 100, and 125. So if I have a mean of 100 and a standard deviation of 16, 100 goes in the middle, and then I would count out 16 for each tick mark. So for 16, if I add 16, that gives me 116, then 132. Let's see, I don't need to go any further because we're doing 85, 100, and 125. If I subtract, that's going to give me 84, and then subtract 16 again, that's going to give me 68. Let's see. So what I'm trying to do is I'm trying to find my standard score for 85. So when X, my raw score, is 85, I want to figure out what my value of Z is, my standard score, which will also tell me how many standard deviations away from the mean I am. Now, because 85 is on the left side of my mean, I'm anticipating that I will get a negative value. And because 84 is one standard deviation away from the mean, it's going to be pretty close to -1. It should be. I'm going to take my raw score, which is 85, subtract my mean, and divide by my standard deviation, which is 16. When I do that, I get Z is -0.9375. So at 85, somewhere really close to 84, this would give me -1 at 84, but at 85, I would be at -0.9375. So I'm just a little bit under 1 standard deviation away from the mean, and that negative tells me I'm on the left side of the mean. Now we have to find the standard score for 100. Well, since 100 is the mean, I know I'm 0 distance from the mean when I'm sitting at the mean. So without doing any work, my Z should be 0. But if you want to do the work, you can see that I would take my 100, which is my raw score, subtract the mean, and divide by the standard deviation, which would give me 0, right? 0 divided by 16 is 0. Okay, last one. When X is 125, I'm anticipating that this should give me a positive Z value because 125 is on the right-hand side of the mean. 125 falls somewhere in here, approximately. So I know it's going to be between 1 standard deviation and 2 standard deviations away from the mean. So my Z should be 1 point something. So when I figure out what Z is, I take my raw score, which is 125, subtract my mean, and divide by my standard deviation. And when I do that, I'm going to get that Z is equal to 1.5625, which is exactly what I thought it should be, somewhere between 1 and 2 standard deviations away from the mean, which would be about 1.5625. Now we're going to talk about percentiles, which is related to standard scores. So once we know what the standard score of a data value is, the properties of the normal distribution allow us to find its percentile in the distribution. And here's what a percentile is. Here's the definition. And the percentile of a data value is the percentage of all the data values in a data set that is less than or equal to it. So, for example, if I said that I took my daughter to the pediatrician for a checkup, and they said for her weight, she was in the 40th percentile. That means there are 40% of kids her age have a weight that is lower than hers or smaller than hers. So when we talk about percentiles, if I said a certain percentile, it's the percentage that is less than at that data value when we're looking at the normal distribution. So looking at it as far as a picture is concerned, if we were looking at the 40th percentile for weight for my daughter, here's 50%, right? That's the center, 50 on the left, 50 on the right. So this would mark the 50th percentile. The 40th percentile means it's this value right here. So there are 40% of kids her age that weigh less than her. So that's why it says it's a percentage of data values that are less than or equal to it. So when we are talking about a percentile, it's the raw score, that data value, so that the percentage that you're talking about is to the left of that data value. 40% of the data values is to the left of that raw value. So, in order to figure out percentages, in order to figure out percentiles, you kind of got to work backwards. And sometimes that's a little bit hard to figure out. So we have a table that we go by, and I'll pull it up in a second and show you how to use it when we go through these examples. So there's a chart in your book in section 6C that's labeled standard scores and percentiles for a normal distribution. Now this table is not as detailed as it would be if you were taking a statistics class. If you were taking a statistics class and we were going much more in depth with this, you would have a lot more data values in this table. These are just some of the key values, so we may have to just pick, if it's not the exact value in the table, we may have to pick just the value that is the closest to it. Okay, so in this example, it says cholesterol levels in men from 18 to 24 years of age are normally distributed. So here's our key word that allows us to use this trick. And it says the mean is 178 and it has a standard deviation of 41. So if we look at the picture, we have a mean of 178, so the mean always goes in the middle, and the standard deviation, I'll label it here, SD standard deviation is 41. In part A, it says what percentile corresponds to a cholesterol level of 190. So if we draw this with our 3 standard deviations, if I go out 41 to the right, I'm going to have 219. If I go out another standard deviation, that's going to be 260. If I go out another standard deviation to the 3rd standard deviation to the right, that gives me 301. Going to the left, I have 137. I have 96. And I have 55. Now, a cholesterol level of 190 is going to fall somewhere between here. Since I know 178 is the center, this is 50% here, so it's going to be more than 50%. What I need to do in order to find something that isn't in our standard deviation of 1, 2, or 3 that we can use that empirical rule, we have to use standard score because it's not an exact standard deviation of 1, 2, or 3. So remember, to find our value of z, we take our raw score, which is 190, subtract our mean, and divide by our standard deviation. And because this is the mean, which has a standard score of 0, and 219 has a standard score of 1, because it's 1 standard deviation out, I know it's going to be maybe something like 0.5, somewhere in there. So when I calculate it, I'm going to get 0.29268,293. So we're less than 1 standard deviation away from the mean on the right, which we knew that. It was going to be between 0 and 1 based on its position on the graph. So now what we're going to do is we're going to figure out what that percentile is by looking it up in the table. This is the table from your book. So we got a z-score of 0.29. So I'm going to try to find the closest z-score that I can to 0.29. Keeping in mind, if you look at this table, it has z-scores that are negative and z-scores that are positive. So you want to make sure that you're picking the one that's positive. And we got a positive z-score of 0.29. The closest one that I can see to that is 0.30. So our percentile is going to be 61.79. That's the closest we can come. So when I go back to this, I know from right here at 190, if I erase this, from 190 over, that's going to be about 61.79%. And we knew based on the picture that it was going to be a little bit more than 50% because it was past the halfway point. It was more than 50% of the graph. So being in the 62nd percentile means, in this case, where we're talking about this problem with the cholesterol, 62% of men between the ages of 18 and 24 years have a cholesterol score at 190 or below 190. I can figure out what percentage is above 190 by just subtracting from 100. If this is about 62% on this side, then this side would be about 38%. So we can say about 38% have a cholesterol above 190, because that would be the blue part here to the right of 190. Okay, the next part says, what cholesterol level corresponds to the 90th percentile? So this time they're giving us the percentile, and we can look up on the chart the closest we can get to the 90th percentile. So here's the percentile column. I want to find the closest I can get to 90%, which looks like this one right here. My z-score for that looks like 1.3. So coming back here, 90th percentile corresponds to a z-value of 1.3. So working backwards, we can figure out what that cholesterol is. Remember, we have that formula. Our z-score is equal to the raw score minus the mean divided by the standard deviation. So if I have a z of 1.3, I'm going to plug that into my formula. I don't know what the raw score is, what my cholesterol level is. That's what I'm looking for. So I'll call that x. I'm going to subtract the mean, which was 178. And I'm going to divide by the standard deviation, which was 41. And I can solve for x now. When I solve for x, I get 231.3. So that means approximately 90% of men between 18 and 24 have a cholesterol level at or lower than 231. Okay, last example says the heights of American women with ages 18 to 24 are normally distributed. So I know we can use these rules with percentiles and empirical rule because it's normally distributed. It says it has a mean of 65 inches and a standard deviation of 2.5 inches. In order to serve in the U.S. Army, women must be between 58 inches and 80 inches tall. So what percentage of women are ineligible to serve based on their height? So if we draw the picture, we have a standard deviation, which is 2.5. The mean is that goes in the center, which is 65 inches. So if you're less than 58 inches, so somewhere over here we have 58 inches. If you're less than 58 inches, which is that tail end, or more than 80 inches, so 80 inches is over here somewhere, so that's the higher tail end. If you're in that shaded area, those extreme values, you're going to be ineligible to serve based on the height. So we need to figure out what percentage those shaded areas represent. So what we can do is we can figure out what their z-scores are. So we can figure out how many standard deviations away from the mean they are, and then we can look it up on the chart. So if x, our raw score, is 58, to find z, we're going to take 58 minus the mean and divide by the standard deviation. And that gives us a z-score of negative 2.8, almost 3 standard deviations away on the left. For the raw score of 80, to find our standard score, we would do 80 minus our mean divided by 2.5, and we're going to get 6. So now what we can do is we can use this to look it up on the chart. So a z-score of negative 2.8, that's right here, gives us a percentile of 0.26. So that means this shaded area to the left represents 0.26 percent of the population. So it's a very small value. Very few people are going to be less than 58 inches high. Now, on the high end, let's look up a z-score of 6. If you notice on this chart, it only goes up to the highest as 3.5. And notice that it's 99.98%. So if this represents a z-score of 6, and the chart only goes up to 3.5, and 3.5 is somewhere in here, and that covers 99, everything to the left of that covers 99.98%. This small wing right here, this little tail, is going to be so small that I wouldn't even count it. I'm going to just count it as 0%. It's so insignificant that I'm not going to count it in our calculations. So I am going to say that 0.26% plus 0% is going to give us about 0.26% of women are going to be ineligible